Hey everyone, this is lecture 2.1 called How Humans Created Climate Change. An alternate title, could this be Wrapping Your Monkey Mind Around Carbon? If you understand that esoteric Buddhist reference, good for you. I have a couple minor disclaimers on this one, just because of how we use language. Um, then we'll talk about what carbon is. We'll talk about how we humans broke the carbon cycle. We'll talk about some of the physical effects of climate change. And actually, now that I'm looking at this, I'm not sure if this is all covered in this lecture. In terms of content warnings, we are talking about some of the negative effects of climate change, but I think this slide is actually more for one of the other lectures around this one, so sorry about that. This is roughly what we're talking about. Oh well. So, anyway though, language is messy. Language is imperfect. So when we talk about carbon, we often talk about how things naturally are or how they're supposed to be. Unfortunately, both of those terms imply that we aren't part of nature. And that division of humans not being part of the world around us is actually kind of what got us in this problem in the first place. So we are part of nature, but we are a part of nature that has come out of balance. Just like sometimes the pH of a lake can just get like really messed up and kill a bunch of fish, whether that's human caused or not. That's kind of what humanity has done to the planet. But what can we do about it? The answer to that is we can do a lot about it. Supposed to be then also implies a degree of intent on the behalf of the universe itself or supernatural beings. If that's part of your worldview, that's cool. But we're not talking about that. We are talking about what our world would be like without humans, right? That's really what we're saying. But using the phrase what it would be like without humans is a mouthful. So this lecture uses a lot of supposed to be. But this brings us to the question that is kind of sparked by other lectures that I've already done at this early point in the course. What exactly is carbon, right? We know that carbon is a problem. We know that climate change is happening, but what exactly does carbon have to do with that, right? Um, that's a question you should definitely ask. And if you haven't asked it, now I hope you are asking it in your brain. So the overly simple question of what is climate change is simply carbon imbalances. And other types of pollution then that do not involve putting carbon in the atmosphere then are likely not part of climate change. There are certain types of air pollution that are, but in general, when we're talking about climate change, we are talking about putting carbon places where it shouldn't go. So, but carbon, and I come from a standpoint of I don't expect you to have taken any chemistry up to this point for this class. Carbon is a very, very common element in the galaxy. Carbon is an intensely common element on our planet, and it is not inherently harmful. You, your dog, all living things on this planet are made out of carbon and combinations of molecules that contain carbon. And so we don't have a carbon problem. We have a carbon in the wrong places problem. There is roughly the same amount of carbon on the planet today as there was 500 years ago. We're not making more carbon, we're putting it places that it doesn't belong. And again, what does it belong even mean? We're putting them places that they weren't before humans did this thing. In other words, water is very helpful to you if you're trying to take a bath. right, and get clean, you don't want to have water in your lungs, right? It's a very similar problem to that, except instead of having water in our lungs, we have carbon in our atmosphere, and that's no good. Now, it should be pointed out that there is almost no raw carbon in the atmosphere. So the closest that we can really get to pure carbon, at least in our day-to-day lives, coal is pretty darn pure carbon. Diamonds are actually also pure carbon. Pencil lead, which actually is not as often graphite as it is actually just carbon in a stick form. This is carbon, right? But that carbon has to get really, really hot to vaporize, like sun type temperatures hot to vaporize. What we have in our atmosphere then is not carbon, but carbon dioxide. And I say carbon dioxide, and that immediately triggers maybe some of those science lessons from elementary school and talking about plants and all that, but then how does that work? So CO2 is the problem. And CO2 is naturally in the atmosphere. But the issue then is that, yeah, CO2 is naturally in the atmosphere, but what we've done is put too much CO2 into the atmosphere, right? We breathe oxygen, and a portion of that oxygen that we breathe, we have turned that into CO2, right? That not only can we not breathe, also heats up the planet in ways that oxygen doesn't. So, when carbon is in the atmosphere without human intervention, plants, and even regardless, plants take in carbon dioxide, via photosynthesis. So, they absorb light and they use the energy that their leaves, and you can't see this, but I'm using my hands to look like leaves, so I guess you could do that if you wanted to be weird like me. They hold their leaves, and plants do move, I don't know if you knew that. They hold their leaves as flat against the sun as they possibly can, so that as much leaf is exposed to the sun as possible, and when that energy is pulled in, that energy allows the plant to suck in the carbon in its leaves, and then that carbon becomes something similar to glucose. I don't think it's the same thing. It basically becomes carbohydrates. Carbohydrates for the plant, right? And plants don't need things like protein the way humans do, not usually anyway. But snacks, basically, is the gist of it, right? Plants eat carbon dioxide, right? Well, you may be saying, I thought plants ate dirt. That's what roots are for. Actually, no. Their vitamins come out of the ground, but like you who might take a vitamin every morning, your vitamin is not most of your food, right? Vitamins are great. Vitamins make a balanced body, but you need effectively what are calories. And the plant's calories are what we would consider air, but is actually carbon dioxide. Oops. Well, I skipped yet another slide. If I remember correctly, that slide was about, well, what do roots do? And there's a picture of a hydroponic plant that I grew in my basement. It was a pepper plant with these big, long roots. And those roots, it's just to illustrate the effort that plants go to pull nutrients out of the ground, but that's not actually what they're eating. They're eating carbon. And here we have another illustration of photosynthesis using leaves and the light that goes onto those leaves, creating carbohydrates for the plant itself, and then also water comes out of the roots as well. So it's not just snacks. I guess it's not just vitamin, it's also drinks, but the snacks come out of the air. So for billions of years on this planet and maybe other places. Could have been happening for longer on other planets. Who knows? Animals breathed out carbon dioxide, and plants ate the carbon dioxide and breathed out oxygen, and then humans breathe in the oxygen, breathe out carbon dioxide. We have a super cool reciprocal system that is regenerative, that allows plants and animals to coexist. And then sometimes we eat some of the plants and sometimes we eat some of the animals, but this thing, without humans screwing it up, could go on forever. And it worked great for a period of time that humans are kind of impossibly not able to comprehend, right? And we, unique, beautiful, highly creative humans, screwed it all up. So, by adding more carbon dioxide to our atmosphere, we are increasing the density of the atmosphere, thus increasing the overall temperature of the planet. So, however, there are also some places then that are getting cooler and getting colder, right? And that also has other negative effects. So the ice caps are getting warmer and melting, but those ice caps held together all the cold air kind of in one spot. But once they melt and the central cold of it all dissipates, then cold air spreads over a farther range of the northern atmosphere as well. And I presume the same is true for the southern atmosphere, but I don't know that air as well as I do our air in the north. So then we're doing this with coal and oil, right? Because that is what we are burning up to put more carbon dioxide in the atmosphere. Yeah, is some of the carbon dioxide being put there by there being more humans than there were before? Yeah, there is. But, and would that be a problem otherwise? Maybe. But really what is causing the tremendously bad problem is our burning of fossil fuels. And let us just remind ourselves that plants and animals collect carbon in our bodies. You've done this the whole time you've been alive. You have been collecting carbon together. And some of it passes through you when you go to the bathroom, etc., right? But your body is a collection of carbon, right? Plants are collections of carbon too. And then when us plants and animals die, every great once in a while, we fall into the mud or under the sea or whatever, and it happens just right so that we get compressed and our carbon gets turned into either oil or gas. Now, the vast majority of life on this planet did not turn into oil or gas. It's just a small fraction of that turned into oil and gas. So this is all to say it really drives home the absolutely non-renewable aspect of oil and gas. And then also, only because I like to be a pedantic prick, I point out that no, oil is not made of dinosaurs. I guess a little bit of it would have been. The vast majority of this then are plants, really. Coal and oil, if you really want to talk about that, mostly plant matter, only a little bit of actual animal matter, but I don't see how that's relevant. Why did I say it? Oh well. So that impact on the Earth cannot be understated in terms of what we have done to this planet, right? It involves other things. Yeah, sure, it involves nuclear waste, chemical waste that isn't carbon, whatever. All that stuff is not good. But what has changed the geology of the planet, and the microplastics are part of it, right? That also will be part of the geology. If we have geologists 20,000 years from today looking back at our time period, they'll probably, when they dig into the earth, notice like a layer of plastic over everything, like little pieces of plastic chunks. That's what the Anthropocene era, that's what we call it. They'll probably call it something different. That's what it'll be identified as, and identified as being. It also, there'll probably be like a degree of soot, of carbon, in this layer of geology that wasn't in other places, right? And it's interesting to note that geologists have been able to determine that the true overproduction of carbon started around 1950 or so, which I mean, there are a lot of people alive today that were alive in 1950. Not most of us, but a whole lot of people. And it was around 1950 or so, and geology can only get really that precise, which is quite precise. That is when we started releasing ridiculous amounts of carbon, right? We were releasing carbon before. Pittsburgh was made a very ugly, carbon-ridden city, as was London, as a lot of places were when the first smokestacks went up. But the true massive amounts of burning fuels, that didn't start till about 50 or so. Additionally then, human population growth, use of atomic weapons did have a part to play there, but the greater part was played in our cars and our all of our generators, etc. I'll jump back then. Our first human cities formed around 7100 BC, right? So we humans had somewhere in the area of about 9,000 years of existing in cities before we started to screw up the atmosphere. And the human species itself, animals that we would recognize as saying, well, you don't necessarily look like me, but you're definitely a person, right? Those creatures go back somewhere in the area of about 500,000 years, right? That's, again, archaeological estimates, but that's a very long period of time. We humans are not inherently harmful to the planet. We really, in the scope of things, just started doing this. But the way we're doing it is intensely dangerous. So to put it into perspective, those early human cities, they had around 10,000 people in them, which by modern city standards are really small. So Marion, Ohio, which is just above central Ohio, they have about 36,000. Columbus, Ohio has close to 900,000, and New York City is 8.5 million. There are cities much larger. I think Seoul, South Korea is one of those mega cities that has like 15 million. I can't remember. But there are other cities bigger than New York, but New York's the biggest city that most of us in this class have been to, so that's kind of my illustration. But by modern standards, though, even those cities were very environmentally friendly because they were using energy sources that were water-based, like water energy or wind energy or animal power energy. They were using what today we would call very sustainable fuel sources that wouldn't actually hurt the planet. They were limited in what they could do, but they were fine for the environment. However, there's a reason why these types of cities never got very big, is because they were ridden and riddled with disease. Because they did not have sewers the way that we understand sewers. Places like Rome, other major cities in the world, they actually had sewage systems if they were powerful and wealthy enough, which were basically big tubes or ditches that they threw their poop into. But modern sewage is not possible without electricity. And I'm getting ahead of myself a little bit, but only by a slide or two. And that electricity pumps water from one place to another. That was one of the very first uses of internal combustion engines, of fossil fuel engines, was to pump water from one place to another. And we figured out really fast, hey, we can move this water, then that means we can move the water in the sewer, so we can move more poop out of the cities, basically. And once we got all the extra poop out of the cities, then cities became places that you could live without fear of dying of some type of terrifying disease like typhus or dysentery, or things that you would hear about in Oregon Trail video games. But when we discovered those fossil fuels in internal combustion engines, it was kind of the beginning of the end, right? And those early cities that did occur well before 1950 really very quickly, over the course of a little less than a decade, became gross, right? And these are pictures of these cities in midday. So, and we don't have color pictures of it, right? But these midday pictures, you can see, I think in this one, yeah, I think that light in the background there might be the sun, because on pictures, yeah, and there's another picture, the sun with the bridge above. That's the Brooklyn Bridge. So you can see the sun in the distance. The sun usually looks quite small in pictures, if you've never, well, actually, anyway. So it was obviously filthy. People weren't stupid, right? But they put up with it because they associated the filth with their livelihood, right? People noticed the dirty air, but they said, well, and they would say things like, well, smells like money, right? And they just kind of put up with it and dealt with it. And there are probably some things in your life right now you are dealing with that will change by the time you're old, and you're going to say, wait, we did what? These are the kinds of things I'm discovering in my early 40s. So, before the 1700s, we did have cities with millions of people, but they weren't burning coal and oil. So this raises the question that I kind of touched on these. Why do we burn coal and oil? What exactly are coal and oil? And why are coal and oil so bad? I talked about what exactly they are. They're old dead animals from millions of years ago. But the reason we burn it is because it burns very, very hot, basically, is the gist, right? Internal combustion engines work because we burn in them fuel sources that burn so hot that, depending on the individual engine, they either are able to vaporize the steam or create micro explosions that move a piston, right? In the case of an old-timey railroad train, you would be turning water into steam, and those were the first ones. Your modern car, if you run a gas car, it's more about micro explosions, but it's the same general principle. We are burning that fossil fuel to move a piston, and then if you can make a gear turn, you can make electricity. That's the gist of it, right? Moving on to the next slide. And yes, absolutely, this picture was taken from like a kid's science fair picture, but it's really good at showing how an internal combustion engine works. So those first engines, as I talked about, was used to move water and keep water out of mines. Well, what were they mining in those mines? Coal. So as we got better engines, we got more coal, we got more engines, we got more coal, and that really built this industry of pulling coal out of the ground, basically. Additionally, then, we became able to build more elaborate sewer systems, and that made our cities bigger. And the bigger a city gets, the more carbon it's going to use. Additionally, then, when we accessed more energy, and this is something Karl Marx talked about in his works. Marx was very critical of capitalism itself, but he also acknowledged that it created a bunch of stuff too. And part of the reason why capitalism was so successful in the 1800s is because the capitalists figured out how to use internal combustion engines to make more stuff, to make more food, to make clothes, metal, wagon wheels, everything. Basically more of everything. And with more of everything, with more clothes, quality of life increased. And people start living longer. And people start living longer, they feel better, they have more kids, then populations grow. And a lot of that time occurred before birth control was common. So you get many, many, many more people kind of in an explosion kind of way. And then in about the early 1960s, in most places, you see that population explosion kind of start to even off because people start using birth control and start having about 2 kids per family. That's kind of usually the average in places that have birth control, but that's beside the point. So then, get back on topic in terms of carbon. Over the last 300 years, we've only been burning these fossil fuels, these concentrated carbon fuels, for about 300 years. We have released hundreds of millions of years worth of carbon into the atmosphere. It's 300 years. In the last 300 years, we have released 300 million, 3 billion, no wait, that's 300 million, I'm messing up my decimal. We have released millions of times more carbon into the atmosphere than we should have, right? 1 million times more than we should have. And that is what's causing the ice caps to melt, what's causing everything to get hotter, cities to flood. Well, no shit. Because there's millions of times more of a gas in the atmosphere than there should be. We put this a different way then, and I think this is a good way to explain it. We understand wood as humans, right? Most places humans have lived, there's been some kind of wood, and those humans have burnt wood, and in burning that wood, we have had fires, and we've basically done that as long as there has ever been a person. We understand that kind of fire. We understand fire good, but fire can be bad, right? But coal and carbon are different. They're a different kind of fire that we don't quite understand, right? Wood is not the same thing as carbon. That's what our brains don't quite get, right? When you burn wood, it releases 1 tree's worth of carbon into the atmosphere. Much less than that, actually, because usually when you burn wood, you're burning much less than 1 whole tree, right? But when you burn coal and oil, you are burning an intensely concentrated carbon, right? And it is comparable to comparing the alcohol content of cough syrup and even like old-timey cough syrups used to have a little alcohol in it. But it's comparing those cough syrups that, like, really it's okay to let kids have them. More or less. Don't make your kids drink. Anyway, it's comparing that cough syrup to like 200 proof moonshine, right? To like rubbing alcohol. It's radically different. It is so much more. It is so much more of a concentration than even like your lightest wine cooler versus a shot of vodka. That's like, those things are far more similar than coal and wood, which is actually really interesting, because that means that if you heat your house with a wood burning stove, you're actually making a good environmentally sound change. And that's very good. And that's actually why wood burning stoves are good for the environment, which is intriguing. That's it for now. Wrap your brain around that, right? We humans have a hard time understanding fire the whole way. So think about those concentrations, do your readings, do our quizzes, and I'll see you next time.